combination reactions, include physical states, and refer to the solubility rules as necessary. So
Okay.
I have barium nitrous
Barium nitrate.
nitrate aqueous plus copper sulfate aqueous turns into barium sulfate, and that's a solid, correct?
Right. Correct.
And then copper nitrate aqueous,
Yeah.
correct?
Almost. The copper nitrate, you'd have parentheses around the NO3 and it'd be twice.
Yes. Oh, I have it on here. Okay. Yeah. Because it makes the coppers a +2. Am I right? So then
Correct.
you swap them out. Okay.
Correct.
Okay.
So there'd be a 2 there.
What the example that I used was because it gives you on predicting and balancing precipitation reactions. I use the last one where you just swap the anions.
Right. Double displacement reaction.
Yes,
Yes.
that's what I used, and it's just really hard. I don't know if I'm going crazy, but I go on here at 5 o'clock in the morning, doctor, and I do walk away for 30 minutes and I'll do something, but I'm here till 10 o'clock trying to figure this out. Am I going crazy? Does that sound about right? You don't get it right away, right?
Right. You're doing good.
Okay. Okay. So I just wanted to know if I understood this, but yeah, I know I need to do a little bit of a balancing. So I'm just going to put the parentheses around the NO3, the NO3 all and a 2 on the bottom. Okay.
Got it. Then you got to balance it.
Yes. It's sometimes a problem takes me like an hour, 30 minutes, but I'm like really trying to work it out. And I know you have to understand the rules too, correct? The solubility rules. That helps.
That or just look
because
that or just look at the table. I gave you that
the
table.
the periodic table or
No, the solubility table. Solubility table.
Oh, yeah. I have that one too.
You can do
Yeah.
that instead of the rules. Use that. It's easier.
Is it? Okay. This one, I know which one you're talking about. This one, correct?
Yep, that's the one.
Okay. And I was using the one the book has too, is this one.
Yeah.
Yeah.
That's the one, but yeah. All right, so the first thing on this is formula mass and percent composition that we're going to do. So formula mass is just how much something's going to weigh per mole. We're going to use our periodic table. We use those numbers that we calculated for each element. So we'll use an example from the book, like let's do Na2CO3, sodium carbonate, Na2CO3. The molecular mass or the formula mass, okay, we're going to use that in all of our calculations. This allows us to convert grams into moles. And all of our chemical equations are in moles. Everything has to go to moles. You can't measure moles in the lab, you measure grams. So this allows us to convert our grams into moles. So what we're going to do is in this chemical formula right here, we have 2 sodiums, right? We have 1 carbon, we have 3 oxygens. Okay. So if we look on the periodic table, sodium weighs, look at on your periodic table.
22.99.
I should be able to go. Yeah, 20, right? Everybody see what it says 22.99? Okay. So roughly 20, well, roughly 23.
23.
If you round that off. So there's 23 for each one. 1 carbon, each carbon weighs 12.011, roughly 12, right? And every oxygen weighs 15.999, which is roughly 16. Everybody see where all those numbers came from?
Yes.
You do it until where all these numbers came from right here. Okay. And then what we're going to do is get 2 times 23 is 46. 1 times 12 is 12. 3 times 16 is, let's see, 16, 32, 42, 48, right? And then we add those together. 8 and 8, 16, 5, 7, 11. So there's 116 grams per mole. That's the molecular weight or the formula weight of sodium carbonate.
I'm getting 106.
Okay. Oh, did I add it wrong? 16,
I'm getting
5, 6, 10. Yep, I did.
Yeah, it's 106.
Yep. 106 grams per mole. So we can use that to convert grams into moles. And we're going to use that when we do our stoichiometry. The first thing to understand is how to do all these conversions. Let's do another one. Let's do iron 2 bromide is in the book here. So iron 2 bromide, iron 2 bromide. So first you have the formula of iron, and that's plus 2, bromides -1. So the formula is FeBr2. So you have to convert the English into chemistry. Okay. And then we have 1 iron, and we have 2 bromides. Iron weighs what? Look at iron, it weighs 55.85.
Yes.
Okay, right. Okay,
So would that be
55.
56?
Yeah, it's close, depending on how accurate we are, but we'll put 56 for now because those numbers are there. And then 2 times bromine. Bromine is?
BR is
79.9, so roughly 80. One times 56 is 56. 2 times 80 is 160. 6, 11, 216 grams for every mole, grams per mole. So that's how you do any compound. You can tell us molecular weight or formula weight, okay, by just using the numbers for the periodic table and how many of each element are in the compound from the chemical formula. Okay. From that, we can use that, like I said, to convert to moles. We can find the percent composition of any compound. Let's take what they use in the book. So that's how I think that's
the mass.
okay. Let's use acetaminophen. Okay, Tylenol as an example.
Tylenol.
Yeah, acetaminophen has a formula. Where am I at? C8H9NO2. C8H9NO2. Okay, so all right. And it wants to know the percent composition of carbon, hydrogen, nitrogen, and oxygen. So what percent composition of it is carbon, of hydrogen, etc. Okay. So we take the whole, we find the whole molecular weight. So we have 8 carbons, we have 9 hydrogens, we have 1 nitrogen, and we have 2 oxygens.
Carbon is 12.01.
Right. Hydrogen is?
Hydrogen is 1.008. So 1.
Yes. So what roughly 1? Nitrogen is?
Nitrogen is 14.1. Okay. And then oxygen is 16.
Oxygen is 16. All right. So we got carbon is 8 times 12, which is 96, right? 9
Yes.
times 1 is 9. I can do that one in my head. 14 times 1 is 14. And 16 times 2 is 32. And we add all those together.
Is okay. That is 151.
151?
Yes.
Okay, so that's our total weight. So the percent composition of each one of these, we just take carbon is 96 out of the 151 times 100, gives a percent. So 96 divided by the 151 times 100.
Yes.
96 divided by 151 times 100 gives you 63 point, let's see, five.
And it's a continual 5. Oh, yeah.
Percent.
It's a continual 5. It's 0.5761589 blah, blah, blah. So I don't know what that would turn into. 63.
Right. So round up to about 3 significant digits. We're roughly at. So 63.6. Is that what you got?
Yeah.
Okay. Perfect. And then your hydrogen composition would be hydrogen is 9 out of the 151. Hydrogen is 9 divided by 151 times 100. That comes out to 5.96, so roughly 6.0%. Let me get that so it's clear here. There we go. Whoa, all the numbers are disappearing. I got a delay here on the, holy cow. Yeah, there's a big lag delay when I don't have my cable on here. All right. So hydrogen, we said was 9 out of the 151 times 100, and that came out to about 6%. Nitrogen. Nitrogen is 14 divided by 151 out of, that's what's out of, times 100. And that equals
9.27,
9.3, right?
9.3.
Okay. I'm just rounding numbers off here, but one place past the decimal. And oxygen
Okay.
would be 32 out of the 151 times 100. And that comes out to what?
32.
21.1.
Yeah. 21.2, right? Because there's a 9 behind it.
Yeah.
I'll put that up. It'll help a lot. Come on, what was that? 20,
9.2. Yeah.
Yeah.
21 point,
21.2.
okay, 20.2. And that's how you do percent composition of anything. You add up your total mass, and then you take the percentage of each part of it. And if you add those together, that should come out to about 100. 69, 79, 89, 99. Yep, and yeah. So that's about, that should total 100%. Or since we rounded off close to it. Okay? But that's how you do formula weight, and that's how you do percent composition. And that's how we usually determine what's in something. We do mass spectrometry. We can tell what's inside of what makes up something. Like in the book, you can show you how cocaine is determined by the weight of each component by its chemical composition. You can determine the chemical composition on a mass spectrometer, and it can tell you what has certain drugs on it. And when you do a drug raid or a bust, you can tell what's in what compound, exactly what it is before you go to court. All right, so the mole concept. So we can convert, like I said, in the lab, we can convert anything into moles. If I have, say we had 18.5 grams of sodium chloride, I can convert that into moles, because to use a chemical formula, you have to get it into moles. Chemical formulas are a molar relationship, not a mass relationship. So it has to convert to moles. So if we had We're gonna start with 18. Like I said, we do all these problems. 18.5 grams. I want to convert that into, that's a question mark. Moles. 18.5 grams. And I have to have grams on the bottom, moles on top. So I have to know how many grams are per mole. So I need to know the molecular weight. So I have 1 sodium and 1 chlorine. The sodium comes in at
22.99.
so roughly 23. Chlorine comes in at
Fluoride is 35.45.
so 35.5, roughly 35 and a half, right in the center there. Okay, so our total mass is going to be 0.5, 58.5. So in our chemical equation here, I know there's 58.5 grams per every mole of NaCl. Okay, so grams cancel, I'm left with moles. And that's how you convert to moles. You're multiplying by 1 still, because 1 mole of sodium chloride weighs exactly 58.5 grams. So we take 18.5 divided by 58.5. Come on, computer. Equals 0.
I thought I was wrong. I got that number and I erased it.
316. So you got 0.316 moles of sodium chloride if we measured out 18.5 grams in the lab. Like I said, so we can measure grams in the lab. We can't measure moles. So we have to convert from grams to moles. That way we can use a chemical equation to predict how much reactor you're going to have, how much stuff you're going to have to use up. All right. So let's see what else do we have. Potassium sulfate. Let's go the other way. Say we have, I'll use one right from your book here. I can get a blank page. There we go. Let's say we have 0.281 moles of potassium sulfate. 0.281 moles of potassium sulfate. You should be able to write these formulas now to convert everything. And it wants to know that is how many grams. It helps me when I'm doing these problems to put it into chemical form so it's in front of my face. Okay, so the word, it'll say how many, if you say you have 0.281 moles of potassium sulfate, how many grams do you have? Write it out so you can see it. Right. So we're starting with 0.281 moles, and I want to convert into grams. Okay. From grams to moles, I know I need my molecular weight. So I know I've got 2 potassiums, 1 sulfur, 4 oxygens. Right?
Yes.
Yes.
Okay. So 2 potassiums, each potassium weighs what?
It's 39.10.
39.1. Each sulfur weighs 32.066, right?
32.06.
So 32.1. And every oxygen weighs 16.
16.
Okay. So 39 times 2 is 78.2. 64.2 and 64. Right? Multiplying those out.
I'm sorry, how did you get 64.2 for the second one? Isn't it 1 times
Okay.
32.1?
32. Oh, I thought that you're right. You're right.
Yeah.
I thought
Okay,
so too.
thank you.
You're right. You're better than I am at this. 32.1. There's only one of those, 4 of those, and 2 of them. Yep. So add those together. We come out to, let's see, 8, 10, 14, 7.
174.3.
Perfect. Yep. 174.3 grams per mole. So now we know to put that on the top this time because of grams, because there's 174.3 grams per every 1 mole. Moles cancel, and we're left with grams. So 0.281 times 174.3. Get your calculators, and it should come out to 48.9. 0.97, so 49.0. Grams, sorry. Okay. But that's our new concept for this chapter. We have to molecular weight and then use that as in conversions. But is that making sense so far?
Yes.
All right, now we're gonna make it harder. Of course. Got to do that, right? Can't just keep making sense.
Wait, how did you get the 49.0 grams? Did you divide 100 and, I mean, my bad, 0.281 divided by 174.3
No, he times
Times
it.
it.
times it.
Remember,
So on the
if it's
other
on,
one, I'm sorry.
go ahead, if it's on the top, you multiply. If it's on the bottom, you divide.
Okay,
So both
because in
of
the
them are
last
top.
one, yeah, in the last one we divided, so that's what I was doing. So you said in the top we multiply and the
Right.
bottom we divide. Okay,
Last time we divided because that's on top, that's on bottom. Okay, so if it, just keep it very simple. So no mistakes. If it's on the top, you hit multiply. If it's on the bottom, you hit divide. So this example was on the bottom. Cassandra's 100% right. It's on the bottom, so we divided. This one though, we were converting moles into grams, which is the opposite. So they were on the top this time. So you have to start with that number. If it's on the top, then you hit multiply. Make sense?
yeah, I just wanted to make sure so I could write down a note about that.
Did we talk about Avogadro's number yet? The
Sorry?
6.022 times 10 to the 23rd?
Oh, I don't think we have.
We talked about Avogadro's number last time.
No,
Okay,
doesn't
good.
sound
Use
familiar.
that right here.
know of.
So I guess
This
we're
is
talking about-
7.2.
Okay, so we talked about. Okay, we talked about moles, right? 1 mole, if you count number of particles, like how much is a dozen?
12.
12.
No, right? A dozen is 12. A gross is 144. Okay, a mole is 6.022 times 10 to the 23rd. That's a mole. Don't get confused with that's all it means. It's just like counting a dozen. You know a dozen is 12. You know a mole is 6.022 times 10 to the 23rd. It's a whole lot of particles. Okay? So that many atoms make up 1 mole. So if I weighed out 12 grams of carbon in the lab, I would have 1 mole. Because from our periodic table, right? So that means I have 6.022 times 10 to the 23rd particles or atoms or molecules of carbon. Okay? It's just parts. It's just a unit of what we have. So whenever you see moles, this is called Avogadro's number. Okay? So whenever you have a mole, we know we have that many atoms or molecules that make it up. If I have 1 mole of water, I have 6.022 times 10 to the 23rd molecules of water. Okay. Now remember, water is H2O. So if I have 1 mole of water, I have 2 moles of hydrogen, 1 mole of oxygen individually, because it's made up of 2 to 1. Okay. So 1 mole of water consists of a 1 mole of the molecule, and it consists of 2 moles of the hydrogen atom and 1 mole of the oxygen atom. That compose it up, that make it up. Because if I broke water into pieces, I would have 2 hydrogens every time I broke it apart and 1 oxygen. Okay. So it tells you the number of atoms or the number of molecules. It depends what you're talking about. Okay. So the next question up here said, well, let's say what's got into that that caused me to do that. Okay. It says a chemist has a sample containing 42.300 grams of sulfur trioxide. How many molecules of sulfur trioxide are present? Okay. So you know sulfur trioxide is sulfur with 3 oxygens. You know it's a covalent compound because they're both nonmetals. So you have to name the subscripts. We never put the mono for the first one. So it's sulfur trioxide. Okay. And it says we have 42.300 grams. So you have 42.300 grams. That's what we have. And we want to know how many molecules.
So you break it apart?
Nope. It says you want to know molecules. A molecule is SO3. If it asks it now, good question. If it asks for oxygen molecules, then you break it apart. If it asks for sulfur molecules, you break it apart. But it asks for molecules of sulfur trioxide.
Okay, so it's of the whole element or, yeah, okay.
So right out in front of us, that's what we got. So we got, now we know we have to get to molecules, we know we have to go to moles. And for moles, we know how many you have per mole. So we need to be able to convert this into the molecular weight. One sulfur, 3 oxygens. Each sulfur weighs 32.1. Each oxygen weighs 16. Everybody see where those numbers are coming from?
Yes.
Okay. So 30.
No, I'm sorry. Where did you get the 5?
No,
Oh,
that's
never
S.
mind.
That's an S.
Yeah, I thought it
That's
was a
sulfur.
5.
Okay, Alex, I know my writings, my office staff, the girls won't give me a pencil or a pen. I have to use a computer to write my notes. They won't let me touch. I can't touch a pencil. I'm not allowed. The only thing I can touch a pencil for is or pen is to sign prescriptions. Other than that, they don't. I have to use a computer because no one can read my writing. All right, so 1 sulfur. So this time won't double it. 1 sulfur is 32.1. 16 oxygens is 1632, 48, right?
48, yes.
So the total is 80.1 grams per mole. So let's do our conversions now. We're starting with 42.300 grams of sulfur trioxide. Now I know how many grams per mole. Now do grams or moles go on the bottom? What goes on the bottom, grams or moles?
You want the desired up
Grams.
top.
Right. You want grams because they cancel. And we know we have 8.1 grams per mole. Now I'm in moles and I want to convert moles into molecules. So moles have to go on the bottom. So moles will cancel. How many molecules are in 1 mole? 6.022 times 10 to the 23rd. Like I said, don't get confused just because it's a big number. It's got to be a big number because atoms are so small. I mean, it's 6 with 23 zeros after it. It's a huge number. But it's just like 1 dozen equals 12. Half a dozen equals 6. 1 mole equals 6.022 times 10 to the 23rd. It's just a number usually to represent that unit. So we got molecules. So if it's on the top, we save the exponents to last. So we'll just save this exponent to later. So to do the math, what I would do is I would take 42.3. So let's do 42.3 divided by 80.1 because it's on the bottom times 6.022 because it's on the top. And that comes out to 3.18. And how many digits do I have? 1, 2, 3, 4, 5 digits. 0, 1, 5, 7, 3. Okay. And I want 5 digits. 1, 2, 3, 4, 5 digits. I want to cut right here. So this number is 5 or greater. So it rounds up. So it comes out to 3.1802. And then bring our times 10 to the 23. Molecules. Not so many molecules you would have. Okay. To get to molecules, you have to go to moles. We go from grams to moles, moles to molecules.
It's funny because when we have like these type of problems like on our homework, like when I see it, I'm like, I'm like a deer in headlights basically, but when you explain
Me
it,
too. Yeah.
Right?
I don't know why, like I feel like it's a terrible thing about being a visual learner too, because like I need like lots of examples in my face in order to understand it.
Me too.
I'm the same exact way. I'm a visual learner. I have to write. That's why you'll see when you ask me a question, I write it in front of me. I have to see it to get it. I'm not the kind of person to go, oh, this is this. I've got to see it. And I've been doing this for many years, so don't feel bad. I've been doing this a long time. And I still make mistakes at it. But it takes practice. And I make it look easy because I just set it up because I know what it's supposed to be. As you practice, you'll get more and more of it. And like I said, if you're a visual learner, which most people are, write it out. That's why I do this. This is the most important step for me right here. That first line. Because I've taken the English and I converted it into chemistry. English doesn't mean anything to me. It doesn't mean anything. But when I put it in chemical terms and put the formulas in front of me, I can see what has to happen. I can see this is my compound. So I know what I can get the molecular weight. I know how much I'm starting with, and I know where I want to end up. And I know to get to the molecules, I have to go through moles. There's an old saying, when in doubt, convert to moles. Because everything revolves around moles in chemistry. You got to get there for all your equations. Okay? Does that make sense?
Yeah, it
Yes.
does.
Okay, perfect. And let's keep going through this section here. Let's see what else I wanted to talk about. Grams to moles. Where's our equation? All right, so let's use the equation. Iron and hydrochloric acid. So if I want to say, the English would say iron, metal, reacts with, not iron, that's an N. Hydrochloric acid is HCl. Okay, and it can produce iron 2.
Is that iron plus hydrochloric acid?
Yeah, iron plus hydrochloric acid. Or I just put with, but that's okay. Iron plus hydrochloric acid goes to iron 2 chloride plus, what else is it going to do on here? Hydrogen gas. So I'm going to take that, convert it into chemistry. I'm going to say iron metal, Fe, plus hydrochloric acid goes to iron 2 chloride plus hydrogen gas. There's my chemical equation. And I want to know if I have if I start off with 235 grams of iron, so I put little arrows there, okay? I want to know how many grams of iron chloride I produce. Let's do that. Okay. So this here is your most important step. This has taken all the English and turned it into a chemical equation. Like I said, I draw arrows, I draw question marks, so I can see what I got. I'm an extreme visual learner. I've got to see it to learn. So iron reacts with hydrochloric acid to produce iron 2 chloride and hydrogen gas. If I reacted 235 grams of iron, how many grams of iron chloride would be produced? That's the English, which means absolutely nothing to me. It doesn't. It's just, it's words. But if I write it down like this, I can see it. I can see I'm going to start with iron. Okay, we start with iron. We go to we react hydrochloric acid. We produce iron chloride and hydrogen. So the first thing we do is balance our chemical equation, and that tells our molar relationships. Okay. So one iron, 2 chlorines. Let's go back to red. We have 2 chlorines, 2 hydrogens, and that's balanced. So what that chemical equation says is 1 mole of iron is going to react with 2 moles of hydrochloric acid to produce 1 mole of iron chloride and 1 mole of hydrogen gas. Okay. So everything is there we need. Let's put 235 grams of iron. That's what we're starting with. And I want to convert that into what? What do you have to convert into to use an equation?
Moles.
Moles. You have to go to moles. Okay? Always, always, always. Grams to moles. And this is grams of iron and moles of iron. So one mole of iron weighs how much? Look at your periodic table. 55.85, right? So 55, let's use the whole thing, 0.85. Okay. And I wrote that completely backwards, didn't I? Hold on. I broke my own rules here. I didn't look at the units because it didn't cancel. So I let erase that. It's working. Okay. No, don't erase my whole line though. It did. No, don't keep going. Stop. All right, iron times. Grams has to go on the bottom so they cancel. Grams of iron and moles of iron. And each gram we said was what, 55.85?
Yes.
Yeah. Okay. So 55.85 moles of iron. Okay, now we go from moles of iron to moles of iron chloride. That's what we want. That's where our question mark is. This is what we want to figure out. Because we know our chemical equation gives us a relationship between moles of iron and moles of iron chloride. What's that relationship? Look at the numbers in front of each one. What is it? What number's in front of the iron? There's nothing there. What is it?
1.
A 1.
Perfect. So I got 1 mole of iron and I got 1 mole of iron chloride. Now I got moles of iron chloride. Now for moles of iron chloride, I can go back to grams of iron chloride. And this is the most common way we're going to do things. So moles of iron chloride goes to grams of iron chloride. And how do we do that? We do the molecular weight. We have 1 iron. We have 2 chlorines. Iron is 55.85. Chlorine is 35.5, right? So 71.
Yes.
Okay. Did I do that right? Yeah, I did that right. So the total is 126.85 grams of iron chloride per mole. So 126.85. Okay, now everybody's gonna look at that and go, that it's absolutely crazy that I did that. But if you look at it step by step, it's everything we've done. We're now just putting it together. And I know it's a lot to incorporate. We'll do a couple more examples so you understand it. Okay? But it's all steps that we've done. Every step we've done before. This is nothing new. It's just putting it together now. This is what I'm starting with, right? We've always done that. This converts grams of irons into moles. This converts grams of moles of iron into moles of iron chloride, which is what I want to see how much I produce. And then I convert this back, iron chloride, into grams. So you're always going to go from grams to moles, moles to moles, moles to grams. And that's how we're going to do it. So what we do is, on our trusty calculators, calculator. All right, we're going to start with 235. And the first number's on the bottom. So what do I hit?
Divide.
Divide. So 235 divide 55.85. And times 1 divided by 1 is just 1. Times, and then times, because the number's on the top, 126.85. And that comes out to 533. And 3 is a 0.7, so 534. 534 grams of iron chloride. And that's how we determine. So I know if I measure out 535 grams of iron, I know I'm going to produce 534 grams of iron chloride. Okay, so I started with 235 grams of iron. I know my end result after I run my reaction is going to be 534 grams of iron chloride. So I can tell how much I'm going to produce before I do the reaction. So I tell the acid reaction to make money. You could also do it for hydrogen gas. How much hydrogen gas are you going to release into the atmosphere? Okay. So let's do another example. Let's make up, let's do, does that kind of make sense?
Yes.
I
Yeah,
know it's not going to make all sense yet, but it will do another. Okay, so let's do another. Let's convert. Let's say we're going to burn, let's see, for methane gas. Methane gas is CH4. We're going to burn methane, and we're going to burn, let's say we burn 87.5 grams of methane gas. How much CO2 is going to be produced? That's a typical question. Okay, we want to know how much CO2 is a greenhouse gas is going to be produced if we burn 87.5 grams of methane gas in our heater. Okay, so turn it into a chemical equation. Methane is CH4, which you'll know that after you do our organic chemistry part. Methane gas plus, what does burn mean? Burn means reacts with what?
H2O.
Not
Or
H2O.
oxygen.
What has he present for burning?
Oxygen.
Perfect, perfect. Oxygen,
I was doing carbon,
all right?
because I was
And
doing
whenever we
that
burn a
problem earlier.
hydrocarbon,
It's
okay? So what's
And then
the resultant?
it's CO2 and H2O.
Okay, so there's your equation. Now I want to balance it. How do we balance it?
So
One carbon, 4 hydrogens.
we have 4 hydrogens over here, so we put 2 in front of the H over there on the right.
Okay,
Hold on, I can't see the screen. So
and how do we balance the oxygen?
The oxygen, do you have 1, 3 on this side? 2,
No,
no?
more than 3.
Oh, sorry, we have 4 on the right side. And we
Perfect.
have 2, so we put 2 in front of the O2 on the left side. So
Now we're
we have-
balanced.
I had this question earlier.
Perfect. So it says we start with, so I would draw an arrow and I would say 87.5. I'm gonna take everything, so I never have to look at my words again. I put everything here and I want to know how much in grams of CO2 I produce. Now everything's there. I don't have to look at the English part anymore. Everything's right in front of me. Okay. So let's start with 87.5 grams of methane gas. And I want to convert that into, you got to go to moles. So we have grams of methane to moles of methane. And carbon, we have 1 carbon. We have 4 hydrogens. 1 carbon is 12, 4 hydrogens is 4. So we have 16 grams per mole, right?
We don't have to do anything with the oxygen.
There's no oxygen yet.
Oh.
This,
Oh,
this is just
okay.
picking methane gas.
Okay.
Yep, there's only carbon and hydrogen. So 16 grams per mole. Now I got moles of, because the grams cancel, I got moles of methane. So moles of methane go on the bottom. And I want to go to what? What do I want to end up with? When that was CO2,
CO2.
right? Perfect. So how many moles of CO2? Look at your chemical equation. I got 1 mole of methane and 1 mole of CO2. And then for moles of CO2, I got to go back to grams of CO2. So I got 1 carbon and I got 2 oxygens. So 12 and 16 times 2 is 32. I got 44. So 44 grams of CO2. So that went from grams to moles. So I use my equation. Then I went to my mole to mole relationship in the equation. Then they converted back to grams. You got to go to moles to use your equation. And it tells you how much is going to react with it. Right? So grams cancel. Moles cancel. Moles of CO2 cancel. And you're left with grams of CO2. So 87.5. Oops. 87.5 divided by 16 times 44 equals 240.6, or so 241 grams of CO2. So if you burn 87.5 grams of methane, you're going to produce 241 grams of carbon dioxide. Does that make sense?
Yeah,
Yeah, I got that.
Good. That's the hardest part right there. Let's pick one from the book that goes a little bit different here. Okay. Let's use, all right, let's do one more again. Well, at least one more. Okay, so the English part says we're gonna react aluminum metal with nitric acid. Okay, and we're gonna produce aluminum nitrate and hydrogen gas.
Not writing.
We're gonna start
Are you
with-
writing?
Was that?
Are you writing? 'Cause
Not
it's
to
not
write
right.
anything yet.
Oh, okay.
Not yet. No, not yet. Okay, let's start, let's say, I'm gonna use, what did they didn't do it with grams, so I'll just use grams. Let's say we're gonna have 212. How would I word the question? Okay, 212 grams of aluminum metal. Aluminum metal reacts with nitric acid, HNO3, and we're going to produce aluminum nitrate. And hydrogen gas.
So how you come up with these equations on the other side, doctor, is you do a single displacement. Am I right or wrong?
For this one, this one would be a little bit different. That's why I'm telling you what it produces. Because we don't have two metals, we have an acid. An acid replaces with a metal. So it is a single displacement, but it's a little bit different because it's not going to, it forms a different compound.
Okay.
So this tells you what it's going to form. And we want to know how much, let's see, how many grams of hydrogen gas? Okay, so that's the English part. It says we're going to react 212 grams of aluminum metal with nitric acid, which is HNO3, and we're going to produce aluminum nitrate and hydrogen gas. And we don't know how much hydrogen gas is going to be produced. Okay, because we're doing this in reaction in a container. If we're producing too much gas, it's going to blow up. Because whenever you have gas being produced in a steel container, you have a bomb. Okay, so it's a good idea to know how much gas we produce that's going to withstand with that container that it's in. Because if you produce too much gas, withstand the pressure in that container, it's going to blow up on you. Okay, so whenever you produce gas in a steel container, you're creating a bomb. So we have got aluminum metal, so Al, plus nitric acid, HNO3. Okay. And it's going to go to aluminum nitrate. What's aluminum nitrate? Nitrate is Al, and then nitrate is NO3. Okay. Aluminum is +3, nitrate is -1. So it takes 3 of those. So Al, NO3 3 times, aluminum nitrate, plus hydrogen gas, H2. So there's your equation. And the first step is to balance it, right? So let's balance it. So we have to have, let's see, we have aluminum balance, we have to have hydrogen 3 moles NO3. So we have to have a 2 in front of there because of the 2 hydrogens, right? But then we have 3 NO3s. So we're going to change that to a 6. I can erase that. So we're going to make this a 6 because we have 2 hydrogens here and we have 3 here. So it's going to end up being 6 to balance it all. So 6 hydrogens, I'm going to put a 3 here. And 6 NO3s, we got to put a 2 here. And we got to put a 2 here. And that should be balanced, right? 2 aluminums, 6 hydrogens, 6 NO3s, 6 NO3 groups. All right. So there's our balanced chemical equation. And we said we're starting with 212 grams of aluminum. And I want to know how much hydrogen gas is being produced in grams. That's not an 8, that's a G. And that's a question mark. Okay, now we do not have to look at our words anymore. This is everything we need right there. Everything's written right in front of you. So we want to know if we put aluminum in nitric acid, how much gas can be produced? Because we're doing like that, we're doing that in a container. That container is going to blow up if too much gas is produced. So we want to know how much gas can be before we start this reaction to see what kind of container we need to hold it. And as you know, hydrogen gas is very explosive. We proved that with the Hindenburg. They filled that with hydrogen gas and look what happened in New Jersey when that thing blew up. Okay? So hydrogen gas will explode. All right. So now everybody should be able to just walk this through step by steps. You're starting with grams. You have to convert to moles to use your chemical equation. We know the relationship between aluminum to hydrogen is 2 to 3. 2 moles of aluminum are going to give you 3 moles of hydrogen gas. And then from moles of hydrogen gas, we go back to grams. Same steps we've always done. So write down what we're starting with. We're starting with 212 grams of aluminum. So I need to convert that into moles of aluminum. We got to get to moles to use our chemical equation. So how many grams of aluminum are in 1 mole? What's aluminum weigh? Aluminum weighs 26.9998, something like that. 27. So aluminum weighs 27 grams per mole. So far, so good?
Yes.
Okay, perfect. And then we're going to go from moles of aluminum to moles of hydrogen gas. Now, I could have gone to moles of nitric acid if I wanted to know how much nitric acid I'm going to use. I could have gone to moles of aluminum nitrate if I wanted to see how many grams of aluminum nitrate I produce. But I wanted to know how many grams of hydrogen I'm producing. So if I look at my chemical equation, what's the number for moles of hydrogen gas? What's the number in front of hydrogen?
So
Six.
is it on both sides?
Let me see.
Is
So
it
would it
6?
be 12?
No, in front of the hydrogen, H2.
Okay.
6?
Not 6. What's my
Oh,
number right here?
3.
3. I got 3 moles of hydrogen. And how many moles of aluminum is that going to react with?
2 moles.
How many moles of aluminum is there?
2.
2. Perfect. That's what my chemical equation says. 3 moles of hydrogen are going to be produced by 2 moles of aluminum. Now I got moles of hydrogen, and I want to go to grams. Now hydrogen is H2, so it's going to be 2 grams of hydrogen gas per mole, because it's H2, and every hydrogen is worth 1. I have 2 hydrogens. That gives me grams of hydrogen. So from grams of aluminum to moles of aluminum, moles of aluminum to moles of hydrogen, moles of hydrogen to grams of hydrogen. So we take 212 divided by 27 times 3 divided by 2 times 2 equals 23.5 grams of hydrogen gas are going to be produced. And there'll be one of these questions on your midterm. I'm not going to put more than one because they take a long time to do. I can't put 3 of these, you never finish your midterm. But there will be one of them on that we have to do this. Okay. But they're all the same steps. You write your balanced chemical equation. Then you go from your grams you start with that you can measure in the lab. You go from grams to moles to moles with your chemical equation, and moles back to grams of what you're looking for. Okay. All right, now we have to make it a little harder. Everybody understands this so far, right?
Yeah,
Okay, we gotta try to confuse you a little bit. Because what we've assumed is we have enough of both of these to react. What if one of these ran out? I mean, say you make sandwiches, you have 2 pieces of bread, piece of cheese, an apple, and then 2 pieces of meat. If you run out of cheese, you can't make the lunch anymore, even though you have more bread and meat and stuff like that. So if you run out of something, your reaction stops. So that's what we have to predict if one of these are going to run out. So let's do, I mean, it's the same basic steps. We're just going to add one simple step to determine it. Okay. So let's take, I don't know. We have to take something we're going to react with. Let me get, let's see what are actually using your book so we can help make it at least easy for you. Let's say phosphorus salt, phosphorus metal, okay, is going to react with chlorine gas to produce phosphorus trichloride. Okay. Let's say we're going to have, this was 32. I'm going to react, I have to make up some numbers here. 32.0 grams of phosphorus. And we're going to run into, say, less grams of this, 18.3 grams of chlorine. How many
Doctor,
grams?
Is this the theoretical percent yield? Is this
Not
the
yet.
theoretical? Oh, okay.
Well, yes, this is theoretical. All we've been doing here, all those examples are theoretical. This is what we would get if everything went 100% correct. But in labs, things don't do that. So we're gonna get what's called a percent yield later in a little bit here. But everything we've done so far is theoretical. It's what we should get if everything runs 100%. Okay.
but
This
this
is
is chapter, I'm sorry.
This is what?
So this is still on chapter 7, right? Because I think I saw this on one of the labs.
Yeah, this is chapter 7. This
Okay.
is your limiting reagent. Okay, the only difference now is we have 2 numbers. We have grams of this and grams of this. So the reaction is going to proceed until one of those runs out. Once one of those runs out, the reaction stops. So you're limited to what you can theoretically make. Okay, just like you're making a sandwich. If you run out of bread, you can't keep making sandwiches, even though you have enough meat. Right?
Yes.
Okay, so if there's 2 things given, you've got to do 1 extra step. And then we'll do the regular one. So we'll do all the regular one after this, but you have to determine which one you're going to run out first. Okay, and we do that through a simple ratio. So the first thing we do is balance our equation because you have to have a balanced equation. Okay, so we have 3 chlorines and 2 chlorines, and 2 and 3 don't match each other, so we'll make 6. Because we know those will match. So if I make this 3 chlorines here, that gives me 6. So that means I put a 2 right there. And then I have to put a 2 right there. So 2 phosphorus, 6 chlorines, 2 phosphorus, 6 chlorines. Okay? So there's my chemical equation. Now, to find my limiting reagent, I have to convert them both into moles because I have to compare moles. You always have to compare moles because it doesn't do any good to compare grams because all your equations are in moles, all your relationships. So let's convert those to moles. So for phosphorus, I have 32 grams. And how many grams per mole? So you look at phosphorus in your periodic table. Phosphorus is 31. 31 grams per mole. So I have 32 grams of it. So 32 divided by 31. Where's my calculator? There it is. So 32 on top, then divide on the bottom, 31 equals 1.03 moles. So 1.03 moles. Okay, and for chlorine, Cl2, I have 18.3 grams. And chlorine is 35.5 for each one. I have two of them. Okay, so 71 grams per mole. So 18.3. Yeah, why did that work? 18.3 divided by 71 comes out to 0.258. Okay. I mean, I got a lot more moles of phosphorus, but the ratios might be different. The numbers might be close. So the way to do it is to set up a ratio. So you set up a ratio of, let's do phosphorus over chlorine. So it's 1.03 over 0.258. That's my ratio. And I'm going to pick one. I'm going to make it set equal. Let's pick phosphorus. So I put phosphorus equal to X, and then I'm going to put my chlorine as 3, because that's my ratio. I got these numbers right here. Okay. I'm going to set one of those equal to X. Or actually, let me back up a second here. It's a 2 to 3 ratio. I got to pick one of these as X. Oh, let me back this up. I'm going to set one of these numbers to my unknown because I know my ratio. All right, so I have 103 for phosphorus. Oh, come on, don't keep going. So I have 1.03 moles for phosphorus, and I can put X moles for my chlorine. And my ratio is going to be phosphorus, which is 2, to chlorine, which is 3. That's my ratio numbers, right? Right from my chemical equation. So I took one of these numbers, even though I know both of them, and I'm just going to put one, and this will work whichever one we pick. Just pick one of them, doesn't make any difference. And then solve the ratio. And that'll tell us how many moles we need. So this says 2x equals 3.09. X equals 3.09 divided by 2. 3.09 divided by 2 equals 1.5. 1.55. Okay, so X equals 1.55. Do I have 1.55 moles of chlorine? No, I've only got 2.258, right? So for this reaction to proceed, I would have to have 1.55 moles of chlorine, and I don't have that much. So this is my limiting reagent. Okay, I just don't have that much. Now, if I would have picked the other one, it would have still worked the same way. If you don't believe me, we'll try it. Okay, so let's go ahead and do the same thing, except this time I'm going to pick X as phosphorus. So I got X moles of phosphorus to 0.258 moles of chlorine. And the ratio is still 2 to 3. And to solve any ratio, just cross multiply. So 2 times 0.58 is 16.5. 0.5, what is it, 0.6? We do the calculation, won't make a mistake here. So 0.258 times 2 equals 0.516 equals 3x. X equals 0.516 divided by 3. And that equals 0.172. Okay, so I need 0.172 moles of, and this one's phosphorus. Do I have 0.172 moles of phosphorus? Yeah, I got extra. I got 1.03. So this tells me that I have extra phosphorus. So that tells me chlorine is my limiting reagent. So either one you pick, just do a simple ratio, cross multiply it, and it'll tell you which one's your limiting reagent. Now we got to eliminate reagent and we go back to the original problem. That's the only extra step. You have to determine which one's going to run out first because now you have two numbers. Okay. So now we start with our limiting reagent because once we're out of that, the reaction stops. So this is what we're going to use right here. So we already went into moles. So I've got 0.258 moles of chlorine gas. I want to go for moles of chlorine gas. And I'm looking for moles of phosphorus trichloride. What's the ratio? Look at my ratio, look at my chemical equation. What do I put for moles of chlorine? What do I put on the bottom here? What number?
Would it be 3?
Perfect. 3. 3 moles of chlorine. What do I put for moles of PCl3?
6?
Not 6. What number is in front of the PCl3?
Oh, 2.
2.
2. Perfect. 2 moles. That's my ratio. 2 moles of PCl3 to 3 moles of Cl2. And now I know how many grams, right? That's what I'm looking for. So now moles of PCl3 to grams of PCl3. Okay, phosphorus was, we have to figure out my molecular weight. I have 1 phosphorus. Phosphorus is 32 grams. And I have 3 chlorines. And 3 chlorines is 35.5 times 3. 35.5 times 3 equals 106.5. Okay. So I end up with 0.5, 8, 138.5. That's my molecular weight of PCl3. So 138.5. Use our calculator. On the top, you multiply the bottom. We take 0.258 and then times 2, divide by 3, times 138.5 equals 23.8 grams of PCl, phosphorus trichloride. So if I were to mix 32 grams of phosphorus metal with 18.3 grams of chlorine gas, I would theoretically come up with 23.8 grams of phosphorus trichloride because I'd run out of chlorine and I'd have extra phosphorus still there. But once the chlorine's gone, that reaction can't keep going. So the only additional step is this little ratio right here. Convert both to moles and set up a ratio according to your chemical equation, 2 to 3. And just pick one as X. Doesn't matter which one, it's still going to work. And then you know your limiting reagent and use that in your equation. So this is the same equation we've been doing, same exact thing, okay? Except now we added another step to limiting reagent. No more steps to add, that's it. We're not going to make it any harder. Okay, this is as tough as it gets. But it got progressively harder. Because you have to think more. Okay? It got longer. You know all these steps though. You know how to set up a ratio. And you know to go from grams to moles, moles to moles, moles to grams. So we get the exact same thing. We just done our conversions. The only thing we added now is we added an extra step of a ratio to try to get a limiting reagent, to tell us which one is going to run out first. Okay? Make sense? Sort of?
Yeah, it's just a lot to take in.
It is. It's a lot.
It
is
is.
a lot. And I make it look easy. I know. It's not as easy as I make it look. You want to do another one?
No.
I think I got the flow.
Okay.
I'm just absorbing it pretty much.
Okay.
Yes.
Yeah, it's a lot to take in. Let's see what else I have here. All we got left is theoretical percent yield. And those are simple just calculations from the formula where we already done. So let's do. Let's pick up. Do one more here. Let's do. Actually, how about one we know? Let's do hydrogen plus oxygen goes to water. Okay. Hydrogen plus oxygen goes to water. Okay. Let's say we mix
Did you bring that purple shirt?
32 grams of hydrogen. And I'm going to mix 5.3 grams of oxygen. Is that right? Or do I do the other way around? 16 grams per mole. No, I want to do it the other way around. Let's make it a little more realistic. Let's do 5.3 grams of hydrogen and 32 grams of oxygen. Okay, run it that way. That'll be a little closer that way. All right. So 5.3 grams of hydrogen, 32 grams of 32.0 grams of oxygen. How many grams of water is being produced? Okay. So you got two values, which means you've got to find out which one runs out first. So convert both to moles. So 5.3, well, first of all, I'm forgetting one step. What am I forgetting to do?
Balance the equation.
Balance the equation. Perfect. So let's balance the equation. All right, so two hydrogen, two oxygens, two oxygens. We gotta put a 2 here.
2.
Okay. And the 2 here. How's that look?
Okay, yeah, it's balanced.
That was good. All right, perfect. So there's our equation. So let's convert grams to moles. So 5.3 grams of hydrogen. And I know I got 2 grams per mole. 2 grams of hydrogen per mole. And oxygen is 16, which is 32 grams per mole. So I have hydrogen is 5.3 divided by 2. Oops, calculator. 5.3 divided by 2 comes out to 2.65 moles of hydrogen. And 32 divided by 32, it worked out pretty good, huh? 32 divided by 32 is 1. 1.00 moles of oxygen. Okay, so let's set up a ratio. Which one you want to pick? You want to pick hydrogen, you want to pick oxygen to be your unknown value?
Ratios instances include leverage, abundance of the chemical elements, slow,
That's
air fuel ratio,
Alexa.
and elasticity.
Stop. I guess something kind of like Alexa triggered my Alexa in the background. All right. So which one you want to pick, hydrogen or oxygen?
Oxygen.
Mhm.
Oxygen,
Oxygen,
you
yeah.
got it. Let's pick oxygen. So I got 2.65 moles of hydrogen. And I got X moles of oxygen. And the ratio is hydrogen, oxygen. Hydrogen is 2. Oxygen is 1, right? From our chemical equation. So cross multiply. First order ratio 2x equals 2.65 X equals 1.325, right? No, that's not right.
I don't,
I'll try to do that in my head, I can't do it. 2.15 divided by 2. Gosh, I'm drawing blanks here for some reason. 2.15 divided by 2 equals 1.075. Okay, so I need 1.075 moles of oxygen. Do I have 1.075 moles of oxygen? How many moles of oxygen do I have?
Doctor, I'm
1.00.
confused.
Right.
Where's the 2.15 coming?
What 2.15?
I thought that's what you said. 2x equals, never mind,
Oh, 2x equals 2.65.
2.65. I understood 2.15. Okay,
And then x equals 1.075. Does that make sense now?
so it's 2 divided by 2.65?
It's
Oh, we're
2.65 divided by 2.
Okay.
Was that?
Nothing.
So cross multiply, you get 2x equals 2.65. So divide 2.65 by 2, you get 1.075. And then you look at their oxygen, and do I have more or less of 1.075?
Less.
Less. So that's my limiting reagent. It's going to run out soon. I don't have 1.075 moles. I only have 1 mole. So this is going to be my limiting reagent. This one runs out first. So there's my limiting reagent. Once I have that, I just set up my equation. And I'm already in moles, so let's just keep it there. So 1.00 moles of oxygen. And I'm going to use my limiting reagent for my equations, because once that runs out, that's it. And I want to go from moles of oxygen to moles of water. And moles of water, it says 2. Moles of oxygen, it says 1. 2 to 1. And then moles of water. I want to go back to grams. That's what I'm looking for, grams of water. And oxygen, we have 2 hydrogens, 1 oxygen. Oxygen is 16, hydrogen is 1. So 16 plus 1 is 18. 18 grams of water for 1 mole. And that will give you grams of water. So 1 times 2 times 18. It gives you 36 grams of water. So if you're going to mix 5.3 grams of hydrogen and 32 grams of oxygen, you're going to theoretically produce 36 grams of water. Okay? So everything is exactly the same, except if you have 2 things, you have to determine which one runs out first. So you got to set up a little ratio. We have to do 1 extra step. And then the one that runs out first is the one we use in a reaction. Because after that runs out, that reaction stops. So we're going to have extra hydrogen. We're going to use up all of our oxygen to produce our 36 grams of water. We're going to have extra hydrogen. About half hour, 40 minutes or so. All right, does that make sense?
Yeah.
I'm sorry, I don't really get
If
I don't
this runs
really
out.
get why you put. Can you guys hear me?
Yeah.
Yeah.
Why what?
What did you where you're trying to okay, where it says 32.0 grams of oxygen and then times mole over 32 grams of
This 32
yeah.
is this 32 right here. Okay. This 32 is from the periodic table.
Okay, got it.
Because oxygen is 16 is O2. That should say O2.
Okay, and then for the other one where it says 2 grams. where it says 5.3
grams.
grams.
Okay?
Yeah,
2
where
grams
does,
per mole,
where
because
does he get that?
hydrogen, every hydrogen is 1. Look at the periodic table. So H2 is 2 grams per mole. So this comes from the periodic table.
Okay.
Oxygen was O2 is 16 times 2. Hydrogen is 1 times 2.
Oh, okay.
It's 1.00795 is hydrogen, right? Okay, no problem. There's a lot of numbers out there.
Yes.
And then for the 18 grams of H2O right there towards the end, how did you get that one again?
18 grams of H2O.
Yeah.
H2O is 2 hydrogens, 1 oxygen. So 2 and 16. Each hydrogen is 1. I have 2 of them. And each oxygen is 16. So that gives me 18 grams per mole for water. That's a 2. Does that make sense?
So you said H2O, 2 hydrogen, 2 oxygen?
1 oxygen, H2O. Remember, if there's nothing here, it's just 1.
So then you multiply the 2 and the 1, and then what else?
No, he's
No,
just
H2O,
adding
yeah.
it. He's
I mean,
adding it.
right.
He's adding
I
the
have
2
an
grams of
H2O,
hydrogen.
I have 2 hydrogens and 1 oxygen, right?
Yeah.
In the compound. Okay. Every oxygen is 16 from the periodic table. Okay. Every hydrogen is 1. So I got 2 times 1 is 2. 16 times 1 is 16.
It's the mass weight is what he's
Yeah,
doing.
the molecular weight.
Yeah.
Of water. You add up the weight of the elements.
Okay, yeah, I was just making sure.
Okay, no problem.
Okay, that makes sense now.
Okay, good.
Yeah, I understood that whole thing. It's just for some reason, like since you're talking so fast, because since I told you like I'm a visual learner, I literally have to write down every step for
Right.
myself and I color coordinate everything so I understand when I'm on my own.
No problem. I think play this in a little bit better signal here. All right. No, no problem at all. All right, so there's one more concept to learn, and that's not going to change any things that we've done. We can still use the same stuff. Everything we've calculated has been what's called a theoretical yield. Come on, computer. Oh, here we go. Which means if we did the reaction and there was no waste and no errors, no nothing, this is theoretically what you would get. If 100% went perfectly, that's the numbers you would get. That's what we can calculate, right? Does everything always go perfectly in life?
No.
No.
It doesn't in chemistry either, okay? So we have what's called a percent yield. And that tells us what yield we actually got. So if we did all this reaction and we determined, we say we did, let's take one of our examples here. Let's take our water. And we said we would get 36 grams of water. Okay, so from the last example we did, we said theoretically we would get 36 grams of water. That's our calculated value, right? Theoretical just means your calculated value. Now say we did the actual experiment in the lab. Say we took 5.3 grams of hydrogen and 32 grams of oxygen, mixed them together, put in a spark and created water. And, and say we got, say 29.7 grams of water that we measured, that was produced. Okay, we should have got 36 if everything went 100%, but nothing, there's always errors, there's always spills, there's always errors and things, there's always mixtures of things that don't go all the way to 100%. So the percent yield is our 29.7, what we actually got, divided by our theoretical yield, times 100. That's it. So we actual yield was, say 29.7, divided by 36, times 100. So we got 82.5%. Okay, that's our percent yield. Okay, so percent yield, I'll put it right here. So percent yield is equal to our actual yield, what we measure in the lab, divided by our calculated or theoretical yield times 100, 100%. That's it. That's the only thing left in the chapter. Okay. So whatever we produce, well, all these calculations we're doing, this is our theoretical yield. This is what we get if everything went right with no errors, no spills, no dropout, nothing goes wrong. Okay. So when we do the experiment in the lab and we actually get a number, it's not going to be quite at a theoretical yield. If you do everything right, it's going to be close. Okay. So we just take what we actually produced, divided by what we calculated, times 100, gives you your percent yield. How accurate, how close your experiment is as obtaining 100% of your benefit. Does that make sense?
Yes.
Yeah.
Yeah, that's an easy part. That's I told him. I'm not going to make it any harder than limiting reagents. That's as hard as we get. All right, questions on this chapter?
No.
Okay. All we got left is 8 and 9 for the midterm. Now, Monday, the 4th of July is Sunday. Okay, I will lecture on Monday if you want me to, because I'm going to have to change Wednesday. My son's getting married in Utah on Wednesday. So I'll be at his wedding Wednesday afternoon. I don't know why he's getting married on a Wednesday, but he is. So I can do it Thursday or Friday next week. I don't know. I don't know why he's doing it on Wednesday. It's crazy. But
So you
I'll
could
be in
do it
Utah
on
on Wednesday. So I can lecture.
the day of the midterm.
So I'll still lecture him. What's it doing the day of the midterm?
I think that's information
All
overload
right, so I can,
right there.
Yeah, it is.
you know, so I can lecture on Monday still. If everybody, is everybody gonna be here on Monday? I know it's
Yeah.
legally a holiday, but it's
Yes.
the 5th.
Yeah,
that
I'll
work?
be here.
Okay, I'll lecture on Monday, and then do you want to do Thursday or Friday?
Thursday.
Thursday.
I'm cool with
Thursday.
Thursday.
Thursday?
Yes.
Okay,
Yeah.
I might be lecturing from my car, but I can do that too. I got internet in the car when we're driving back. So that while we drive back on Thursday, hopefully leave early in the morning. So Thursday it's still 6 o'clock and Monday is 6 o'clock. Does that work?
Yes.
Okay.
Yeah.
So I won't be doing Wednesday. So no Wednesday next week, but I will do Monday and Thursday, 6 o'clock.
Okay.
Okay.
Monday.
Sounds good.
Sounds good.
Okay.
The same link?
Okay. Other questions?
Is it gonna be the same link?
Saying no, I will send you the new link.
Okay.
Monday will be the same link.
Right,
I will send a new link for Thursday's meeting.
okay.
Okay, I'll send it out this weekend. I'll get everything straightened out. So I'm leaving for Utah tomorrow, but I'll still be, I mean, you still email me, ask me questions. I can still get on Zoom. So we're all good on the internet once I get there. And then my wife's going to do the wedding. So she's setting all that up. So it'll be interesting. All right, other questions? So you got that straight. I'll do Monday and Thursday.
Okay, so you said for the midterm, it's 4 hours, right? And
The midterm
then,
is 3 hours and 10 minutes, I think it was. 190 minutes. I can double check here. I can double check by doing this, actually. Let me double check it real quick here. It will be on the Monday, and it will be Come on, computer. Midterm. Okay, it's going to be available July 9th between 12:01 a.m. to 11:59 p.m. So 24 hours basically. And it's 190 minutes. So 63 is 180. So 3 hours and 10 minutes. And it's 71 questions. Worth 150 points.
And so we just like, since you said it's multiple choice, right?
No, it'll be true, false, multiple choice, and matching.
Matching. Oh, okay.
And
So-
it'll be fun, some fill in the blanks, like round off this number and you'll write it in the blank. You'll type it in the answer. But be really
Oh,
careful when you
okay.
type in your answers. Only put, it'll tell you, only put in numbers. Do not put in a capital O for a zero. Computer will not understand that. Be really careful with that. Use zeros. Don't use the capital O for a zero.
Okay.
You see what I mean? Because the
Yeah.
computer, the computer will say it's an O, it's not a zero, and mark it wrong. Okay, but so fill in the blank ones will tell you, we'll give you specific examples of what to do. Like I'll put CO2, it'll say name the compound, put carbon dioxide. It'll say no capital letters, spell each one correctly, and just put carbon one word, dioxide the other word.
Okay.
Okay, that's what it'll be like. Yeah, you have 3 hours until, so you have, once you start the midterm, then you get 3 hours and 10 minutes, then it turns off. So start it when you have a block. You can't keep going back and forth to it. You love it. 3 hour and 10 minute block. So anytime that's convenient for you in that 24 hours will work out fine.
So can you go back and forth to the questions or it's
Yes.
just answer?
Yes.
Yes. Okay.
You go back and forth to the questions.
Okay. Because in anatomy, they don't like to go back and forth.
No? That makes it really
You-
hard.
Yeah, you answer the question and you're done. Next question.
Oh.
It does make it very hard.
Yeah. When I had anatomy, she would just show us the questions and then she would move on after 5 minutes. So I would take pictures of the questions if I could go back and write it down on my paper because we wrote down the answers on paper. Because I don't think
Yeah.
5 minutes is enough for 5 questions.
She gives us 10.
At a time.
That's hard.
12 minutes for 10 questions.
All right. So like I said, since everything correctly.
Are we
Perfect.
done with
Okay,
this?
other questions?
Are we done with this chapter?
We're done with that chapter, yeah.
No, that was fast.
Yeah,
It was a
that's chapter
short
7.
one.
Yeah, it's short, but there's a lot of information in there though. And I'm also putting together a study guide too. And I'll have that out. I'll email you the study guide before, I'll probably do it the next day or two to help
For the midterm?
Okay.
for the midterm,
Is
yeah.
this? Okay, thank you.
I'll email out the study guide. So let me write all this down, what I have to do. I'll forget. So I want to email study guide. I want to email the study guide and the new Zoom meeting number. And we're going to go on Thursday at 6 o'clock. Okay, perfect. All right, back to questions again. Any questions? This chapter or any of the chapters before this? Or up in front of this too, if you're going ahead.
I have questions, but I emailed them to you. I don't know if you received them.
I didn't get it. When did you email them?
5:30.
Oh, I was already online here. Yeah, I didn't get them yet, but I can pull up my emails here.
Okay, thank you.
Let's close that so that doesn't pop up. And then there you go. It's still recording, which is good. Got it, perfect. All right. I can see some ping files. Read the thermometer, report the temperature, the number of correctional digits. Okay, if you look at, most people can't see the picture, but if you look at the thermometer, let me see if I can share this screen with you. Right, chat doesn't pop up either if I do this. Okay. And screen 1 and 1. Okay, everybody should be able to see the thermometer here with the 70 degrees.
Yes.
Okay, if you're looking for the
Yeah.
degrees, it's to be 70, would be right here. This bottom line is 70, right? See my mouse?
Yeah.
This is not, okay, that's 70, 71, 72, 73, 74, almost 75. So 74.9, I would say. That's why 74.1 is incorrect. So that'd be like 70, that's almost 75. Just below it, you can get about 74.9.
Okay.
Does that make sense?
Yeah.
Okay. Okay, that's one. And let's get. Oops, came up again. Why did it do that? Okay, there we go. Perform the calculation, record the answer to the correct number of significant figures. Okay, so you have 34.123 plus 7.90. So let's, I'll have to do that on a piece of paper, then move it out of here. All right, so put in your calculator, 34.123. Let's see, where's my calculator? 34.123 plus 7.90. 42.023. Now you can round this off at the end or during. I usually round it off during it. I'm 2 places past the decimal. So it's 42.02 I get for the top number. The bottom number, I get 98. Let's see, 98.7654. 7654 minus 8.666. Something like that. Comes out to 90.0. I'm good till 3 places past the decimal. So I get 90 point, where am I at? 099. I'm good to 3 places past the decimal. So 90.099. That's 3 places past the decimal, right? Yeah. So my top number is 42.02. My bottom number is 90.099. So I take 42.02 divided by 90.099, and that comes out to 0.466375888. And I am good to 4 significant digits, my top number. So 1, 2, 3, 4. So the answer comes out to 0.4664 is what I get.
I'm sorry, what is it?
Does that mean? I got 0.4664. I'm
Okay.
good to 4 significant digits.
Okay, that makes sense. Why I got
Make
it.
sense?
Yeah, because I didn't include the 4 after the 6.
Right. Because it's
Okay,
good to
but
4
why-
significant digits.
Why are you getting 4 significant digits?
Because the top number is 42.02.
So
And the bottom number is
7.
90.099.
I
So my top number after I do the addition is 4 significant digits. Because I'm good at 2 places past the decimal. My bottom number is 5 significant digits. So I use the smallest one.
Yeah. See, I thought it was 3 because of the 7.90.
Yes, exactly what I was gonna tell you. I would have put the same answer as you.
No, because that tells you you're 2 places past the decimal. Then you do your multiplication division, then you use the number of significant digits. Remember, adding and subtracting are different rules. Adding and subtracting is the least accurate number. So adding and subtracting, you're good to however many places past the decimal you are. Multiplying and dividing, you're only good to the number of significant digits. Does that make sense?
Yeah.
Okay. All right, let's do, that was. And. Okay, what's the longest length? You want to go longest to shortest, right? Longest to shortest, shortest, man, I can't talk. All right, so if you look at that, let's convert everything into the same units. So let's convert everything into meters, okay? So 100 inches, we'll put 100 inches, and there's 2.54 centimeters per inch, and centimeters is 10 to the minus 2 meters. Okay. That will convert that into meters. 10 feet, there's 3.28 feet per meter. That goes to meters. And 1,000 meters is in meters. And nanometers. 1 times 10 to the 11th nanometers. Nanometers 10 to the minus 9. So nanometers on the bottom, 10 to the minus 9. And that comes out to meters. So 100 inches. Take 100 times 2.54 equals 254 times 10 to the negative 2. So it's 2.54 meters. So 100 inches is 2.54 meters. Okay. 10 feet divided by 3.28 is 3.05 meters. Then you got 1,000 meters. And then we've got 10 to the minus 10 to the minus 9 is 100 meters. Okay, so if you convert all those to meters, 100 inches is 2.54. 10 feet is 3.65. 1,000 meters, and then 100 meters. So the two bottom ones need to be switched if we convert everything into meters. Okay, you got to convert everything into the same to compare them. You got to compare apples to apples. Does that make sense?
Yeah, it does.
Okay.
Thank you.
Because 1 times 10,000 nanometers is 100 meters, and that's less than 1,000 meters. So it would be 100 inches, 10 feet, 1 times 10 to the 11th nanometers, and then 1,000 meters for the correct way to put it. Okay?
Thank you.
Oh, no problem. And everybody should be able to see the questions coming up. Hey, Alton, what's up?
Hi.
What's up, buddy? Okay, determine which statements are consistent with Dalton's atomic theory. Oh, I'm trying to remember its exact theory. Chemical reactions combine two different elements in specific ratios from compounds. Oh, to form compounds. Chemical reactions combine different elements in specific ratios. That's true. Atoms of the same element have identical properties. Atoms of different elements have different properties. Okay. All matter is made of atoms. Atoms cannot be divided or destroyed. Well, in chemical reactions, that's true. Inconsistent. Atoms of one element cannot be converted into atoms of another element. Okay. Atoms of one element can be converted to atoms of another. Atoms of one element cannot be converted into atoms of another element. The top one here under inconsistent is consistent. That's true.
Okay. So the other ones are right?
Atoms of one element cannot be converted. Was that?
The other ones under consistent
I
are
didn't
right?
hear you.
The ones I have under
They
consistent,
seem right to me, yeah.
okay.
Yeah, this one should be consistent also, this top one. 'Cause
Okay.
that's inconsistent. That's inconsistent. That's inconsistent. Yeah, these bottom three are inconsistent, but the top one's right. Atoms of one element cannot be converted to atoms of another element. Not through chemical reactions, they can.
Okay, so that's the only one that's
So I
wrong?
would say those. That's what I'd say.
Okay.
Yeah, I put that over the consistent ones. Okay?
Okay.
Because all the other last, those three are false. That one's true on the top. You can't convert them. You can't turn lead into gold with chemical. You can with nuclear reactions. You can't with chemical reactions. You can turn lead into gold with a nuclear reaction. You can change element, but not with a chemical reaction. There's no way. You cannot split the atom with a chemical reaction. So you cannot change it. That's why you get conservation of mass to balance our equations. And there is one more. Identify the exact numbers. 56.00 seconds. That's a measurement, right? That's not an exact number. The number of centimeters, that's an exact number. That's a conversion number. 1 inch is two, and that's not a measured value. 1 inch is 2.54 centimeters. Just like the speed of light is 3.00 times 10 to the 8 meters per second. Okay. So the top one is a measured value, so it's not exact. The 2.54 centimeters is an exact number. That's what is in 1 inch. Okay, that's our conversion. That's not a measured value. 3 pounds, the weight of an object, that's a measured value. And 4 choices, okay? 4 choices is an exact number. Okay? If you have 4 choices, you can't have 3.75982 choices. You got 4. Just like you have 28 people in the classroom, you got 28. That's an exact number. There is no rounding off. Okay, it's an infinite number of zeros. Okay, so exact numbers would be 2.54 and your 4 choices. The inexact numbers or your measured values would be your 56 seconds and your 3 pounds. You weighed 3 pounds.
Okay.
Does that make sense?
Yeah, it does.
Okay,
Thank you.
perfect. Those are your questions. No problem. Other questions?
I have questions on chapter 6.
Okay, I lost my iPad connection here, I think. Okay. Let's see if I can share this again. Hopefully. Oh, come on. Maybe it'll work. We're running an air connection here, so hopefully it'll work. There we go. Look at that, Alton. It seemed to work, didn't it? All right. Thank you. But we're back in business. Okay, what's your question?
Okay, so mine says write the balanced chemical equation for the reaction shown, right?
Okay.
And it shows this. It shows, can you see it?
No. Can you read it to me or not?
That's the thing. I don't know how to decipher it. It says carbon, nitrogen,
Okay,
chlorine, and hydrogen.
Let me stop the screen share again. All right, put it up again so I can see. Whoa.
Like too bright.
Oh, okay. Carbon is gray. Nitrogen is blue. Chlorine is green. And hydrogen is small. So it wants to compare. What does it want to do?
It wants to write the balanced chemical equation for the reaction shown. So when I saw that, I was like,
Okay.
kind of confused.
Okay, put it up again. Let's take a look. Hold it up to the screen. Let's take a good look at it. All right, let it balance.
Okay.
All right, so we're starting with it looks like there's 3 compounds of, it's got to come in.
Too bright?
Yeah, it's not
Can you zoom in
reflecting
more?
too much.
Why don't you share your screen?
There
My
you go.
screen.
Can you,
See it?
With your computer?
it's because on her phone. I'm not going.
I have-
I'm gonna-
I have the same problem. I could read it to you.
Okay, but look, I can just see what it, okay, there's, go ahead and say something, Cassandra, because it puts you back on my big screen.
Okay.
Okay, there you go. Now put your phone up again.
Okay.
Yeah, I know, it's hard to do off a phone. Okay, hold it right there. So I've got N2 and then Cl4. And I've got 3 of those. And I've got 1, 2, 3 carbon with 4 hydrogens plus CH4 3 times. Okay, and the other one I've got, looks like hydrogen gas, 1, 2, 3, 1, 2, 3, 4, 6 hydrogen gas, H2, and then 3 nitrogen gas. And what are the green things? It's carbon with 4
Fluoride.
chlorines? 3 carbons and 4 chlorines. Carbon tetrachloride. Okay, I think I got it. So if you look at the left side, those are your reactants. You see where the nitrogens, it says we have 3 nitrogens. Those are the blue ones, right?
Yes.
Yeah.
So your reaction would be 3. Let me put it on here. Let me see if I can share my screen again. Get back to my iPad. Okay. All right. All right. So it said I had 3 nitrogens, which is those ones are just the 2 ones combined, the NCl forms, right? There's 2 nitrogen dots and 3 and 4 chlorine dots. There's 3 of those in there, and there's 3 CH4s. Okay, that's on the left side. There's a carbon with 4 hydrogens around it, and there's 3 of those. There's a nitrogen. There's 2 nitrogens with 4 chlorines around them, and there's 3 of those. And the other side, it should be 6 hydrogens and 3 nitrogen gases, just N2s, and 3 carbon tetrachlorides. Okay, so you look at the key on the bottom, shows you which elements are there and then which ones are combining. And if you look at the balanced equation, that should balance. 12 hydrogens, 12 hydrogens, 6 nitrogens, 6 nitrogens, 3 carbons, 4 chlorine, 12 chlorines, 12 chlorines. And that's a balanced chemical equation. That's what we talk about. You can't create or destroy the atoms. So you gotta have the same atoms on the left as you do on the right, the same number. That's a balanced chemical equation. And that's all that was saying. That's how to write that out. Does that make sense?
Thing part is just the for that one to write it out.
Right.
I was just like, okay, that's crazy. So I didn't know what to do.
Yeah. But you just look at the key and you see there's the 2 nitrogens with 4 chlorines around it. And there's 3 of those molecules.
Oh,
you look
okay.
at one
Yeah, I
carbon
just didn't
with
know
4
how to read
hydrogens.
it. That's why.
Right. Yeah, it's kind of weird, but that's what it says. Does that make sense now?
Yeah.
Okay. Phew. We got through that one. Hard to see that one. Where are you going, Alton? Okay, other questions?
Yeah, I had one more on chapter 6.
Okay.
Yeah, it's asking me about precipitation reactions.
Okay.
So I was like, okay, what is that?
Precipitation is
So-
when solid forms from 2 liquids. You take 2 liquids, you mix them together and a solid forms. We got that from our solubility chart.
Okay.
Okay, that's a
So it's-
precipitant.
So it says for number 20 on chapter 6, it says AgNO3
Okay,
aqueous plus NaCl aqueous is what? And then we have to complete and balance it.
okay. Okay, so you double displace your reactions. Remember, this is your positive side, your negative side, positive side, negative side, and you switch them. So Ag is the positive, so it combines with the negative of the other one. So you get AgCl. Na is the positive here, it combines with the negative here, you get NaNO3. This was +1, this was -1, so that's good. This is +1, this is -1, so that's it. So is that balanced?
Yeah.
Perfect. There's your equation. Now you have to determine which, so these are aqueous and these are aqueous. And you got to determine which is aqueous on the right side. So look at your look at your solubility chart and look at Ag, which is silver, and then nitrate, which is NO3. This is nitrate right here. So silver nitrate is a solid. That's a precipitate. Sodium acetate, there's sodium and acetate is aqueous. So we go back to our, where did it go? Oh, I lost it. How did I lose it? Oh, there it is. It was going too fast. It went past me. All right. Oh, that's not it. Come on. Where'd he go? I lost everything. Boy, I don't know where this thing goes on this computer, but all right. Okay, so we had AgNO3 plus
Aqueous
NaCl
plus
went to AgCl plus
NaNO3.
NaNO3. So this was aqueous and this was our solid. Okay, so that's our precipitate. And there's your balanced equation.
So, okay,
Now,
so
from
then
that
when we,
equation, go ahead.
sorry. So then
No,
when
it's
we
okay, go
write it, we just write the first part and then we just write the AgCl and not include the NaNO3 because it's not a precipitate.
No, you still write it because it's still ions in solution.
Okay.
But now, if you want to write like the net ionic equation, then you would write the total ionic equation. We did this, Ag plus NO3 minus plus Na plus Cl minus, because those are all dissolved. They don't have to precipitate. AgCl does not break apart, forms a solid, plus Na plus NO3 minus. Now remember, you got spectator ions, which in this case is NO3, same on both sides, and Na plus. So those are your spectator ions, which you'll have to identify on the midterm. You'll have one equation to identify spectator ions. And your net ionic equation is Ag plus Cl minus goes to AgCl. Okay, that's your net ionic equation. But this is your total molecular equation. This is a total ionic equation. So depending what they're asking for, depending what you have to include when you write it out. Okay. For the precipitate is when two clear liquids mix and then a solid is formed. And you got to predict which one forms a solid from that solubility chart. Does that make sense?
Yeah.
Okay.
And there's another part of that question where it said K3PO4 aqueous plus MgCl2 aqueous is what? So it's asking us the same
Maybe it is
thing.
what?
It's asking to complete and balance the precipitation reaction.
Okay. KCl and Mg phosphate. Mg is 2, so Mg3 PO4 twice. That's a 4. Okay, so there's your equation. You got to balance it. So you put a 3 in front of the mg, put a 6 in front of here, 2 in front of there, and is that balanced? 2 PO4s, 2 PO4s, 6 potassiums, 6 potassiums, 3 mgs, 3 mgs, and 6 chlorine, 6 chlorine. Okay, there's your balanced equation. In KCl, that's aqueous. And magnesium phosphate, I don't know. Magnesium phosphate, let's look at magnesium. And let's look at phosphate. Magnesium phosphate is a solid. So that's your precipitate for that reaction. I don't know why that disappeared, something like that. Dang. Oh, I saw it a second ago. There you go. And this is your solid. So this is your precipitate. And everything else is aqueous. Because you look it up on that solubility table. Look at magnesium, look at phosphate, and when it combines, it forms a solid. Remember, S means precipitate, solid. AQ means it's aqueous. That means it dissolves, breaks apart, forms ions.